Hello, folks. So today we'll be talking about the importance of rotation while testing range versus rate or rate versus range and other tests. And we are fortunate to have two outstanding speakers, Lee Chinitz, our CTO, and Dan Dabrowski, our principal systems engineer. So Lee is going to present some background, and Dan is going to run the demo. Lee, both guys have had lots of experience in the Wi-Fi industry and wireless industry in general. Lee has been with key companies including Casa Systems, Cisco, and Motorola. And he has been involved with standards activities including FCC, IEEE, Wi-Fi Alliance, TIA, and ITU. He holds 20 patents. And Dan has been in the wireless industry since 2004, again in important companies such as Sierra Wireless, Huawei, and Airgain. And Dan has a strong RF background and has a lot of knowledge in how Wi-Fi testing works. So with that, I'm going to hand it over to Lee. Oh, by the way, just while we are presenting, feel free to raise your hand if you have a question or type the question into the Q&A. And we'll try to make pauses every slide or two slides and involve you guys if there are any questions.
Great. Okay. Thanks, Fanny. I would also like to welcome everyone. Thanks for taking some time out to join us in this new way of working. We're hoping to give you an interesting hour in which to think about something other than, for example, COVID-19. We've been, as Fanny said, doing these seminars. This is our second one. We plan to do more of them. And what we wanted to do also was take a little time at the beginning here, some questions that came up in the last seminar, in case any of you are repeat attendees or want to watch the video of the last one. In general, what our seminars are about is how to do wireless testing using the octoScope personal test bed, and how to make the environment in which you're doing testing more realistic to model the environment in which the devices will actually be used. What we talked about last week was our Multipath Emulator. This is a device that we use to do actually what the name of the device is, to emulate the kind of multipath environment that the devices would be in when they're in, say, a home or small office. When that session was going on, we got a question about the Multipath Emulator and how it's related to our ability to do MIMO testing in general in the Octobox. We wanted to expand on that a little bit here. It's a logical question to ask whether or not the Multipath Emulator is needed in order to do MIMO, since in most people's minds, MIMO is really enabled by having multipath in the environment. The answer to the question, though, is no. The Multipath Emulator is not required, and this kind of explains why. In the environment in which we test, the way MIMO works, right? You have multiple transmitters and multiple receivers, and different information can be sent from the different transmitters, can be received by those multiple receivers, and with some sort of complex math, you can actually separate those as long as the paths between the various transmitters and receivers are separable. And so this is a picture of what that looks like. You can see essentially there's a path from every transmitter to every receiver. So that creates basically a matrix of equations that refer to the path between the transmitter and the receivers. And like I said, it's some interesting and complicated math that lets you separate those out. What's important to recognize, though, is that matrix, the physical manifestation of that matrix, actually happens over the air in the octoScope testbed. the octoScope test bed were designed for doing over-the-air testing, and so all the signal mixing that's required in order to make the matrix actually happens in the box. It's not done by the Multipath emulator. It's actually done by the air links in the box. The Multipath emulator is actually adding a little bit longer delays, something again to make it a little more realistic in terms of looking like a home or small office. But the matrix itself is made over the air. We're able to do MIMO testing in the box with or without the MPE. That leads us to a discussion of how we can create those separable paths. And the way we do that is by having control over the location of the test antennas in the box. We can put those antennas all around the device, kind of wherever we want to. And we can even put them in such a way that we create an over-the-air version of a Butler matrix in which the antennas would be 90 degrees separated from each other. That looks a little bit like this, and what I'm doing in this slide actually is giving a bit of a preview to some upcoming seminar discussions that we'll have. And I'm not going to dwell on this topic at all. I'm just going to say this, and for anybody who's intrigued, please join us probably as early as next week when we'll talk about this in more detail. But we have a test element that we call a PAL box. And that PAL box is full of what we call stay PALs. Each of those stay PALs is an endpoint device, and there are 16 of them in one of those boxes. The way that that entire system is cabled into the chamber where we have the device under test looks like this, and you can see sets of 4 of those stay PAL test devices are all connected to different sets, different pairs of antennas. We arrange those pairs of antennas in the corner of the box. And so as you can see, we're now spread around the device under test. We're at 90 degrees, if you were to kind of draw that out. And so this is the sort of the equivalent of a Butler matrix over the air. That's what that looks like in a picture. Here's what it looks like in an actual photograph. And you're going to see a lot more things that look like this today. You'll see the inside of our chamber. You'll see devices actually moving as we do some of the demos today. But what you're seeing in this picture is how the system is configured, just like shown in the previous slide. You can see these red circles are highlighting those pairs of antennas in the corner. And over here on the right-hand side, we're showing a custom bracket that we've created to allow the antennas to be easily mounted in the corners. Another question we had last week related to the MPE was around the time variability aspect. There was a question about whether or not it did vary over time, and we answered that it does not. It's a static frequency fading channel that's shown here in the picture on the right. But it is possible to cause some degree of time variation by using elements of the test bed that actually can allow things to move a bit. And specifically, and the topic of this week's conversation is the built-in turntable. So by putting a device under test on the turntable, we can actually add some motion to the device, so add a bit of Doppler and change the relationship of the test antennas and the probe antennas, thereby changing the multipath environment. So that takes us right up to the topic for this week, which is testing using the turntable, the reasons for it and how we do that. So I'm going to go back and talk a little bit about something that's very important to people who are doing wireless testing, probably people who do testing of any sort, which is that whatever test tools you're using, for example, the test bed that we're talking about, it's very important that those test tools be able to produce results that are both repeatable and reproducible. Because when you're doing tests, if you run a test and then run it again, you get the same results, that's a very good thing. You have a lot of confidence then in what you're doing and what your results are. If you run a test and you run it again and you don't get the same results, that can be a little bit discouraging. But if you do have confidence in your test tools, then at the very least what you know is that it's your device that you're testing which is somehow varying or unstable. But if you don't have confidence in that test environment, then you're really left with more questions than answers. Do you have a problem with your device under test? Do you have a problem with your test bed? So as the test vendor, it's very important to us to make sure that we are very confident in the stability of the test bed. And the turntable, as I'm going to describe, is an element that can be used to really help make that possible. I mentioned on that slide the words repeatability and reproducibility. It's probably a good idea that we get on in the same page about what we mean by those. So when we talk about them internally, by repeatability, we mean the ability to run tests over and over again, changing nothing between the tests, and to get the same results. Those are repeatable tests. That means that the test bed, with no changes being made to it, is stable. Reproducibility is a bit harder, but what that means is the ability to reproduce tests taken either in a different test bed, a different but similar test bed, or in the same test bed but at different times after something has varied in the test bed. Maybe the device under test has been moved, maybe the test bed was configured for a different test and then reconfigured. So both of those are important. And both of them are a function of both the device under test and the test equipment. The device under test is the thing we're looking at, so we definitely want to understand how that performs, but the test equipment is what we're responsible for, and that is the one that we need to know is stable. So what we're going to do for the rest of this seminar is to talk a little bit about how we can set up tests and run them so that we do have confidence in both the repeatability and the reproducibility. And we're going to talk a lot about a kind of test that is fairly well known, and we refer to it as the rate versus range test. I'm going to describe that for anybody who isn't completely aware of what it means. It'll be useful just because we're going to talk about it so much. So it's a classic wireless test, and it is essentially the emulation of a user walking away from an access point. So as the user walks away from the access point, obviously the distance between the user and the access point increases, so the attenuation of the signal increases, and that will affect the throughput. When we just look at what that looks like, a measurement looks like as a function of time, it looks something like this. The top flat part is as the user is fairly close and starting to walk away, and then as the user reaches a certain point, the link will have degraded to the point where it can no longer maintain the maximum throughput, and the throughput starts to slowly decline until some point where you've walked so far away that you simply have no throughput left. That's one way of looking at the data. A more common way of looking at the data is to kind of average the data points for any given attenuation setting. This would be roughly equivalent to a person standing a certain distance away from the access point and measuring for a certain period of time, then moving a little bit further away and measuring, moving a little bit further away, et cetera, and measuring. And when that person measures for a certain period of time, we then would average the data together and we get a plot like this. This is the classic rate versus range plot. We'll have a lot of them during the discussion today. Another way of looking at the data, of course, is to look at pretty much the same data on the throughput side, but instead of as a function of attenuation, look at it as a function of something that's even more physically meaningful, which is the signal level being received by the user. This tells you how far in signal level you can go before the signal degrades so far that you can't even get any throughput at all.
Excuse me, Lee, we have a question from Benny about our degree of repeatability within a specific throughput range. I think you're going to address it a little bit further on, right?
Yeah, I have some data there. Hi, Benny, by the way. We'll address it there. And if you have more questions about it, we can try and answer them. And then we can always, and this is for everybody, any even more detailed questions that we can't get to during the presentation, we'll be happy to handle offline. So you just contact us with those.
And by the way, folks, when Lee was showing a person stepping away and standing to measure for some period of time, like 1 minute is common, that can also be done with the turntable rotating at that one spot for 1 minute. And so that's exactly what we're going to show you later on.
Right.
We also have someone who has a question. Their hand's up. Let me unmute you. Bajendra, I think you just need to unmute yourself.
I think if you can go back to the previous slide. Yeah, so this is the same question I have last time also. So the question we have from the previous, so many people have asked about this question. Like we have this octoBox, and as you can see in the graph saying that the performance degrade as you can adding the attenuation, and that your RSSI also decrease going forward if you move forward, right? So like that particular modem, how is that, how much is his capacity, like how long the person can go from away from that box till he get no throughput, everything is dead. So people want to know the distance exactly. If there's no, it's like a no clear, no furniture and stuff like that, just a clear line of sight. And if you have some furniture and other that can absorb RF signal, how much the distance it will be. So is there anything, some calculation is there?
Yeah, there is actually, and maybe we can take it offline. I can show you a little bit about that. But this plot, the one in the upper right, is actually very easily convertible into a distance, and everything you said there is completely appropriate, right? So, a path loss model, a wireless path loss model, depends on the frequency of operation and the distance, and then the environment in which you're doing the measurement. So, if you know the transmit power of the device under test, and you've measured the RSSI here, then you know the path loss. And the path loss can be, as I said, converted into distance just by defining the path loss model that you want to use. If you're using, as you said right at the beginning, nothing around, so roughly a free space model, you would simply convert path loss into distance as long as you know the frequency. And if you have a specific environment, like chairs and tables and things like that, you would simply modify the path loss model based on kind of measurements people have done indoors to describe what a path loss model looks like indoors, and you can convert from path loss to distance based on the path loss model. I can show you some of that.
Okay, thank you.
Okay, so the question for us as the vendor of the test tool is, how can we make sure that the results are in fact stable, or at least the test bed itself is stable? There's two sources of instability or sensitivity in measurements that we really want to address here today. There's some more which I'll touch on briefly, but one of them that we want to focus on is what we call positional sensitivity. So this means that if you have the device under test in the test bed and you move it, translate it relative to the test antennas, so further from or closer to the test antennas, that can cause differences in the results. And that's what we're showing here. So now you'll recognize this rate versus range plot. And the blue curve here shows this is a rate versus range plot that was gathered when the the device under test was fairly close to the antennas, and then the orange one is what happened when we moved it away from the antennas. So you can see that it changes the relationship of the device under test, the antennas, changes the multipath environment, changes the results. The other aspect of sensitivity we want to discuss is what we call orientation sensitivity. So this is not just a translation, but just an orientation as we rotate the device again relative to the test antennas. What the picture on the right is showing you is how antenna patterns have shapes and are very variable. This is not one of our test antennas or even a test antenna of a Wi-Fi device, but it's just showing how antenna patterns can be can have very different shapes in different directions. That's really the point there. And the kinds of things that our customers are often testing with MIMO antenna arrays. There will be peaks and nulls in the pattern, kind of represented by that moving blob there on the right. And if you then rotate the device around, you can move from a peak in the pattern to a null in the pattern, and the device itself can start adapting that pattern based on how it's now seeing the test antennas. So again, orientation can also change the multipath environment and have an impact on the results. So let's focus on the two aspects that I defined earlier, repeatability and reproducibility. So in the repeatability case, we shouldn't have any of those issues. We shouldn't have rotated anything. We shouldn't have moved anything. The definition of repeatability is that we do a test and then we do it again. And hopefully, Benny, this gets to at least part of your question. So there are other things in a wireless testbed that could cause even results done with no changes at all to not be repeatable. And the octoScope testbed has been specifically designed to eliminate those. So, for example, if there was interference coming into the testbed, changing the environment, that would be a problem. But we are the sort of industry-leading shielding in the system that we have. If there were waves inside the environment that coming from the device under test that were, say, bouncing back and forth off of the walls and interfering with each other and creating standing waves, that would also be a problem. It would make the environment very sensitive. But we have a semi-anechoic environment with a lot of absorption, and we don't have that issue either. Another problem that is sometimes seen in test beds is that even if the environment itself appears to be shielded, if other devices are being connected into that environment through ports that are not themselves shielded, there are paths right into the test environment for external interference. We've also taken care of that problem. So, we've done a lot of things, including making all of our tests completely automatable so that it's not necessary to touch any of the devices in order to run or rerun tests. And as a result, what we see is high repeatability in our test bed. So this is an example. This is some data of 5 rate versus range tests taken one after the other without moving or changing anything. It can actually be difficult to see that there are 5 runs there, but there are. The data for them is shown in that little box on the upper right. So it's data taken at multiple attenuations and 5 different times. And the variation that's there is an average of the coefficient of variation, which is on the right-hand side. It's extremely low. It refers to the fact that the standard deviation of each of those points is extremely low compared to the value of the point itself. So what we have is very, very sharp and repeatable measurements at each point. I guess there's a lot of things I see popping up, so we'll take a pause here.
Yeah, there is a question from Martin. And I guess you have an answer on your slide, but I'll read it anyway because maybe we want to elaborate. It says, while aiming for maximum repeatability, we will observe statistical variation in test results. What statistical variability should we expect? And what are the root causes of statistical variability? So I would say what we're concerned with, as Lee's pointing out here, is to give you very repeatable chamber antennas, etc. Some of the repeatability will come from device itself, how it adapts. And we see some devices completely repeatable, and those will be mature devices. Our experience is at the beginning of a new technology cycle, like Wi-Fi 6 right now, we do see a little more adaptation uncertainty. We see issues. If you have a mature kind of legacy product, you should be able to see very repeatable results like this. And I don't know, Lee, if you want to add to that.
No, I think that's good. That's right. All right. So then the next topic was reproducibility, right? This is the one where, again, you have example would be a company with labs in different parts of the world who would like to be able to do similar tests and get hopefully, the same or similar data. A group, somebody trying to reproduce a test that was done some time ago. A good example of that would be regression testing. So, device is tested, then weeks, months later, new software, you want to run those tests again. Sometimes it's necessary to touch or move the dot during the testing process because, there's something that's not automatable. You need to actually, physically touch the device. So there's many reasons why you can't, always just do tests and do them multiple times and not move anything. So reproducibility is very important, and with some care, it is possible to get the environment itself as close as you possibly can to what was done the last time. But it's also true that using the turntable is a really good way of averaging out the effects of any variations that will continue to exist even after you've been as careful as possible. So when we talk about the turntable, we're talking about this element in the test bed. Again, it is, it's built right in. It's completely controlled via automation, and works just like any of the other devices in the test bed. So now let me describe to you a little bit about what it can do for you. So I showed this picture before where we took some data with one device and it was moved between the two tests. If we do that same test and we move the device during, between tests, but in each test we actually rotate the device while we're doing the test, you can see that the gap between the two measurements closes up almost completely. And this is why the use of rotation is so powerful, because it really helps to average out the overall, the effect of any orientation or positional differences between tests. Sometimes when we're talking about this with customers, they'll ask us, what do we think? Is that a good way to do these tests? And our answer actually is yes, that averaging over angles during the test actually makes a lot of sense, because for the most part, that's how people will interact with the devices. People will either be moving around and experiencing the device from multiple directions, or to tie back to last week's meeting, or last week's seminar, even in the case where a person's not moving, when they're in an environment like this, they're going to be receiving multiple paths from the device, and those paths are actually emanating from the device at various angles, and then bouncing off walls and other reflectors in the environment. So it's really the performance of the device kind of as an average around its area where it's supposed to perform that makes a lot of sense. And for that reason, you know, one of the industry leaders in the testing of Wi-Fi devices for homes and small businesses, SmallNet Builder, does testing exactly that way. I've provided a link here to the description of, you know, how we test wireless devices or wireless products. You can see in the image that they actually, you know, call out the turntable. And if you look on the left-hand side, you can see in the description of how tests are done that, you know, the turntable is called out very specifically. It's, you know, set to a certain position, and then during the test, it's run through a full 360 degrees while the test is ongoing. So it's for all the reasons that, you know, I've tried to describe here, that we do have the turntable built into the test bed. And we have a number of different ways to use it, and those are all visible if you were to look at our UI, which you will be doing actually quite a bit. So let me explain the three primary ways of using the turntable. So the first is the one I just showed you from SmallNet Builder. We call that RvR while rotating. So that's our rate versus range, and we do that while rotating. And as Fanny mentioned before, it's actually something commonly done in open, you know, like home testing as well. Devices will be put on a turntable, and while you know, a walk test is being done, for example, the device itself will be rotating around. That is a good way of getting, again, as I said, averaging out the effects of position and orientation. In a test like that, we don't actually record any angular information. That's not the point of the test. The point is just to use it as an averaging device. And one example, and that what SmallNet Builder called out, is to run a test and do a complete rotation for every attenuation value. There are two other tests where we actually do record the angular information, and I'll describe those here just so you're clear on what's happening as we do the demos. One is the one we call rate versus range versus orientation. So in that one, we go to a certain position of the device, and we do a rate versus range test, a complete rate versus range test. Then we move to another orientation and do another rate versus range test. So that can be a bit of a stress test for the device because the testing device, there's a point during the test at which the testing device moves from being essentially quite far from the device to very close to the device, and it happens very quickly. I'll show you what I mean by that in just a minute. And then there's another variant of that test that we call rate versus orientation versus range, or RvOvR in our nomenclature. And in that case, we do a complete rotation at every attenuation point. And this one doesn't have the jumping effect. And I will show you what I mean by that. Take a little pause. I think I saw a hand. If not, I will move on. Okay, I'm going to move on here. So the first one of those, the rate versus range versus orientation test, again, this is the one that has a bit of a jump, and you'll see what I mean. What we're doing here essentially is emulating a person walking away from the device, and then whoop, they jump right back to the device and walk away, but in a different direction. Okay, so this is what a rate versus range versus orientation test looks like, and this is what the data from a test like that would look like. You'll recognize now these rate versus range plots. You'll see sort of that classic shape, and this is all of that data for one angle or one orientation, and then here's the data for the next and the data for the next, and again, we have the point at which we've essentially walked extremely far away and then magically appeared right next to the device again. A rate versus orientation versus range test, RvOvR, works a little bit differently. In this one, we're essentially emulating a user walking in a circle around the device at a certain distance, then moving a little further and walking around, moving a little further, walking around again, moving further, walking around again. And then finally, the test is over. You've moved so far away that you're at the end of the range. So in this case, as you can see, we don't have that jump. We have what essentially looks like one big rate versus range plot, we have all of the data from all of the angles for specific range or orientation. And we move to the next range and then the next range. So the data, though, because we are recording the orientation data, looks something like this. In a polar plot like this, right, we have throughput plotted radially. You can see the throughput going from 0 up to 1800 megabits per second. Around the edges, you can see the angles, and then the different colored lines correspond to the throughput as a function of orientation for the different ranges. So the big one on the outside is the closest to the device, and then the blue one is moving further, and the orange one is moving further than that. Was there a question there? I guess you guys will let me know. We'll keep going. So built into the octoBox itself is the turntable, as we've mentioned now a number of times, as well as all of the software required to create the 4 tests that I've just described. Rate versus range by itself, rate versus range plus rotation, which is the small net builder test, rate versus range versus orientation, and the rate versus orientation versus range, the 2 variants that I just described. When you choose anything that includes the turntable, you'll see our tools come up, which will show you the turntable position and give you access to the controls for the speed and the start and the stop angles, you know, everything you need. And you'll see all this in real time, so I won't dwell on it here. I just will point out one other thing that you should notice while you're watching these demos, which is that another source of potential variability in the tests would be if the turntable were to bind up the cables and start dragging the device around in the box. So you'll also be able to see the careful construction that we have that lets us avoid any cable tangling and keep the results, again, repeatable and reproducible. So with that, I am going to turn this presentation over to Dan, who's going to show you some real-time live demos of what we just discussed.
Awesome. Thanks, Lee. So here we go. So as Lee mentioned, there are multiple ways to configure a test using the turntable, and all have different distinct characteristics and purposes. So we're going to start with the range versus rate with orientation test and show the device rotating during measurement collection. So hopefully we can see right now the device inside the test chamber rotating, so we can kind of get an idea of what it's doing visually while we're taking this measurement. The DUT is an ASUS AX1100 or 11,000 tri-band device that's transmitting in the 5 gigahertz band. It rotates around the axis in 360 degrees, and the speed in which it rotates is precisely calculated based on the step duration. You can see that the device is rotating at about 6 degrees per second because we set the test duration for 60 seconds. So it'll rotate at this, and we can rotate up to a speed of 10 rotations per minute. So yeah, I'll actually switch from this view to actually show the UI, and we can kind of get a view of it too. I just wanted you to see what we were looking at inside the chamber when we were.
So I would just add there is a mode of the test. For example, you set the test at each point to run for a minute.
Yeah.
And if you say enable rotation, it will calculate RPM speed so that in that 1 minute on the attenuator step, your device will rotate 360 degrees. So every single orientation will have been averaged in that 1 minute.
Yep, that's exactly correct. So I'm going to show this in our UI, and right now we'll start the measurement. And we've set the test up to run with 0 dB of attenuation to start. We're going to go to 30 dB of attenuation in 15 dB steps. And after the first step, we're going to be using a non-line of sight threshold, which will actually turn the test into a non-line of sight test after this measurement.
This is for those folks who may not have been at the last session last week. Non-line of sight is done by our Multipath Emulator, and we can switch from line of sight to non-line of sight automatically, and that models crossing across a wall.
Yep. So here we are. We're looking at the, we can look and see the fire rate up here at 11AX fire rate of 2400. We're seeing that the MCS level is at 11. We can see that because the device is rotating, some of the throughput isn't as static as we saw earlier in Lee's slides. We can see a little bit of movement. And now actually we see once the device hit the minute mark and is beginning its rotation back, our attenuators have stepped up, and now we've crossed that line of sight into non-line of sight threshold. And we can see the device kind of scaling back and forth to try to push the most traffic as it can. Another good thing is that while we are showing all these KPIs, we're showing the RSSI, the data rate, the MCS, the streams, we're showing bandwidth. We can also show a whole host of other metrics while we're measuring if they pertain to your test. We can show data rate, data RSSI per chain. We're showing up top. Speed tests.
Yeah, put on the speed test. That could be fun.
Yeah, let's go see. So there we go. So we can kind of see what we're running, like you would get if you set this test up on one of your devices at home. So it's kind of a good visual that helps you kind of see how much variability there is as you're rotating and as the chipset is trying to scale and push that traffic through. And a really good site I can change right here, I believe is there we go, is that once we look at this whole test right here, this whole minute-long test is actually averaged down to 1 point. And we can get that number, and then it'll actually provide one of these numbers for each minute-long step. So it's really powerful for taking and condensing all that averaging out, like Lee was talking about earlier. So we'll let this finish up here.
Dan, we do have a question from Bajendra. Let me unmute you here.
No problem.
So just one quick question. So do you mention this is only for 5 gigahertz, you said, right?
No, this test is for 5 gigahertz, but we can run it for any for 2.4 or any channel that we support.
So can we do like combine also? It's just like a 2.5, 5 and combine?
Yes, you can actually run concurrent. You can define as many traffic pairs as you need on the left. And we actually did a seminar where we ran with 16 different devices.
Oh, okay.
Yeah. And we'll probably go and show that next time because we'll be talking about OVDMA.
Okay, just one comment. Okay, thank you.
Yeah, no problem. Yeah, this was just highlighting another building block within the Stack Max Octobox test system. So now we can actually switch and show the. Go ahead.
I'm sorry, we did have one more question from. This is from Ravi.
No problem.
Ravi, you're unmuted.
Hi. I want to know what's the difference between the rotation and the orientation. How do you test the orientation or it's a rotation? So right now, whatever showed is the rotation.
Yeah, that's a good thing. I think Lee touched on it earlier. When the rotation test, when you have the plus rotation, that means the device is constantly rotating, and it's not collecting angular data. It's purely there to kind of average out any of the orientation or positioning inconsistencies you may have in your measurement. Whereas the rate versus range versus orientation, or the rate versus orientation versus range are really orientation dependent measurements, and you can get the polar plots and the data out of it. And I'll actually pull that up right here, and you can kind of see that immediately once we go over, you can see that there is a plot, and we will start populating this plot when we start running a measurement.
So even while doing the orientation, it's still going to rotate there will be the turntable will keep rotating it?
No, we actually just step it and leave it in that orientation and run the test at each orientation. So it's a demo coming right up.
Oh, okay. All right.
Yeah, yeah, and I'll actually pull over to that right now, just so we can look at what another view of the rate versus orientation versus range. So let me pull up that video. Make sure it's going this time. Okay, I think it's going.
So we
now,
have a question while you're playing it. Can we do 900 megahertz range? The answer is yes, we can. Anything down to, well, we like to say 700, but we have customers using it down to 600 and lower, even at 300 megahertz. You just need different antennas. These high gain antennas you see here go down to 2 gigahertz, but we do have other antennas for 900 megahertz range.
Yep. Yep, and no problem. So yeah, right here we're just seeing that this is actually the device rotating, stopping, and we can configure how long it stops at each orientation. We can configure how long the settling time is. There's a lot. It's highly configurable, and I'll actually go switch back to the UI and show that test right here. Just want to show you that it does stop and then switch and measure. Okay, great. So I'm going to change my step duration to kind of speed this up a little bit. And then my training interval is where it's going to be settling after each rotation. Okay, great. So yeah, now we have the range versus orientation versus rate, which like we saw earlier was taking a measurement at a specific orientation with a specific attenuation. Right now we're starting at 0, and it's going to continue measuring all the way around in 30-degree steps, because that's what we set it up as. You can see over here, and it's going to go all the way through, come all the way back to home, change the attenuation, and then do it again. Now this is good because it avoids what Lee was talking about earlier with the jumping effect. If you just wanted to see the overall total range of your Wi-Fi device, you want to know the capacity of it to measure at a certain range, like you were talking about before, you can kind of get an idea of that before you rotate over an entire measurement field. So yeah, so we can, we'll actually look over here and see that this is perfect to show. Is that when you look over on the right-hand side and you see the data rate or the MCS, and you see this dip, and also in the throughput, it's cyclical. So you can see that it happens every single time that it rotates. So in order to get this to stop, we'd probably change our training interval to a little bit more so we don't see that kind of dip. But it is showing the device moving and recovering back to the proper rate. So it's a good.
Yeah, so this is actually a good place to explain the training interval. You can set it to not use those dips in your average. So
Yes.
Those points are average, and if you want to give it some settling time before you actually use the throughput measurement, that's what that settling time is for. And we have that for each attenuation step or each turntable step. And we even have training period when you start traffic, because sometimes TCP there's some dynamics that it'll start lower or higher and settle to something. So you can take all that out of your results. You can just say, this is my training time, don't count it in the average.
Absolutely, and it's different for every device. I kind of wanted to include it in here so you can see that some of these might not be included if you don't use an octobox.
It's included. It's always on the plot. It's just not included in the calculation.
Exactly. But I was saying, as far as if you don't have the insights into these kind of KPIs, if you're measuring over the air in a test house per se, you may not notice that it's because of the movement of the turntable. Whereas here, we can actually keep checking and changing the training interval, so these will kind of go away. And actually now we can see that the device went back. We're getting our second attenuation point, and we'll continue going all the way through, measuring through to 360 at that point, under the same test setup that we had before with the non-line of sight. So this was the line of sight up here at the 1800 megabits per second throughput, and then down here about the 950 is after the non-line of sight. So we actually have one more measurement. I won't let this go all the way through, and that was the range versus rate versus orientation. And we have a video that speeds this up a bit because it is kind of long and dry. So let me pull that up. Okay, great. Pull this up here really quick. 1 second. Awesome. Okay, so the last type of test that we're showing here is the range versus rate versus orientation. This is measuring 3 different attenuation points and then rotating the device around the orientation. So you can kind of see that it's rotating around. Yeah, it took a little second. Yeah, okay, sorry, some technical difficulties. But yeah, what we weren't seeing before is last test, we were going all the way around and measuring every orientation before we switched attenuation levels. Now we're measuring at each point, we're measuring the 3 different attenuations, and you're getting that kind of jumping effect. If you look down at the throughput, you're kind of seeing it jump down and scale back up. And this is really critical if you want to stress the chipset and make sure that it recovers to those 11AX data rates, MCS levels, and even streams. So you can kind of make sure that you're trying to have as much bandwidth as possible in the highest MCS levels throughout the whole test. But yeah, I guess this is the third and final rotation-based measurement. So I will throw this back to Lee to kind of close things out. But yeah, if there's any more questions, feel free to ask and we'll be able to answer those.
Okay, so yeah, we're coming very close to the end of this now. As we mentioned before, this is an ongoing series of seminars that we're using to help people while we can't get out and visit you in person, or you can't visit us in person, to see our systems and understand how they work. We are doing all of them using one of our standard configurations, which is the one shown on this slide. It's the we call it the Stack Max. It's essentially kind of a maximally sized test bed that has pretty much a superset of all of the functionality that's of most interest to most of our customers. It's made up of a number of different elements. The MPEs that are shown here in the middle, these horizontal boxes, those are the multipath emulators, and they're the devices that were the subject of last week's conversation. I already teased a bit the PAL box, which is down here on the lower right-hand side. That's the one that has 16 state PALs in it, and we mentioned that we'll be talking about that quite a bit in our next seminar, so watch out for that. And the big one up top here, this is the chamber with the turntable in it. You can see on the picture on the left here, you can see the turntable with the device under test mounted on it. So as we go through the seminars, we will essentially be exercising more and more of the Stack Max, showing what it can do, and going through a lot of the different tests. Again, last week we used the MPE just to talk about non-line of sight and line of sight propagation. This week we've added the turntable here on the left-hand side. and the path that we had was from there through to one of the stay pals in that group of 16 over here on the upper right. Again, we will be adding to, as you follow this through with us on this series, we'll be adding more and more of the pieces and doing more and more testing. So next week, as we've mentioned already now, we will be focusing on testing for OFDMA. That's going to use that PAL box, those stay pals. We'll have a lot more devices in the link. Somebody asked a question about simultaneous, traffic and multiple bands. We probably won't be doing multiple bands, but we'll certainly be doing multiple traffic streams. So please join us for that. And any questions that you have, you can send to the email address shown here. If you'd like to see us cover anything in the seminars, give us your thoughts there as well. And we can hang out for a little bit and take some questions. So
yeah, there are a couple of questions. So the easy one is, will we be publishing recording? The answer is yes, we will be. And then you have a question about maximum attenuation that the device can be set to. So our attenuators are set to our 90 dB range in half a dB step. So our range in the testbed is pretty much from saturation to disconnection. So you can really torture your device.
And remember that the attenuator is not the only source of attenuation in the link. Again, we are an over-the-air testbed, so typically the link will contain an over-the-air link from the device under test to the test antennas. In the system we were just showing you, that attenuation was probably another 25 to 30 dB of loss. So we're talking about being able to get, even without anything else in the link, over 100 dB of attenuation.
Right. Another question, Lee, can we put a client on the turntable and do similar tests?
Yep, we should probably just say that because we had the exact same question in an earlier version of this seminar. So the answer is certainly yes. We talked about the test quite a bit from the point of view of an access point being the device under test, but that's not a requirement. It's just more for the ease of conversation. But if you look at this configuration here, this device on the left, on the right-hand side, that's labeled PAL6. That's our Wi-Fi 6 version of our test device, our PAL test device. That could be, for example, configured as an access point, and there could be a station device under test on the turntable over here, for example. That's just one possible configuration, but yeah, we're not limited to testing only access points.
And of course, our PAL6, which is also in the PAL box, it's an access point chipset. So when you use a station device under test, we have an access point partner for it.
And we have a raised hand here from Magendra again. Let's see.
So I have one last question. So we have this octoBox, maybe it's a very older one or something like that. So we've been using this octoBox and then using landslide to pass traffic. So that's a different Spirent tool. The demonstration that you guys have done is really, I like all the dashboard in one. So is that like a traffic also can be controlled by some platform that you guys have, like a video while the DUT is in the chamber, and then you guys are doing some traffic testing like that? So it's like in-house testing tool also inbuilt in this chassis or something like that?
Who wants that one? Fanny, you or me?
You can take it, Lee.
So the answer is yes. We have our own built-in traffic generator. We call that traffic generator Multiperf. Multiperf is a tool that is starting to incorporate more and more functionality. It has, underneath it, aspects of iPerf, actually iPerf 3, was the primary traffic generator. We are bringing in some aspects of iPerf2 because there's some functionality in iPerf2 that's not in iPerf3. We have the ability to run ping, and we're also starting to bring in some application level traffic as well. So, yeah, the built-in tool that we have, Multiperf, is what allows us to do a lot of what you saw there in terms of being able to, run traffic, gather statistics, display them. As far as even going beyond that, our devices have bridging capability, and it is possible, and we have customers who do this, to actually use them to run traffic, but generate, let's say, the traffic runs through them, but we're generating, real traffic by bridging out to actual, say, the internet on one side and a video streaming device on the other, something like that.
Can we also simulate like how many user we can add? Say, suppose like 5 user, how is the performance like that?
Yeah. Actually, so that's actually the easier part of what we do. So the PAL 6, for example, over here, Fanny mentioned, right? It's a real AP chipset. One of the things that we do to that chipset, though, is we add other functionality, and one piece of that functionality is what's called virtual stations. So this thing can simulate up to, if you use all of the radios, I think the number is 96 virtual stations. So if you're looking to test capacity, for example, on an access point, you could create something like 96 virtual clients, and you can run traffic to each of them. We mentioned this before. You can create, essentially an unlimited number of traffic pairs. So each one would have its own IP address. Each one would have its own traffic stream, but they would essentially be virtually created here. The stay pals that I mentioned before are actually separate radios. So there's 16 of those in that box. So you could use those to load up either in conjunction with the 96 or separately. So yeah, we have a lot of capability for capacity testing.
I would say not just separate radios, but there's separate Linux and Windows machines there. 16 of them. Plus, you can add real off-the-shelf devices like you see on the left. And so you'll be able to combine off-the-shelf devices with virtual devices with instrumented station devices for OFDMA. So it's a very powerful platform. You can really bombard your device under test with a lot of different traffic. And as Lee mentioned, bridged video and voice. Another thing Multiperf does is multi-point to multi-point testing. So that can be very interesting in setting up kind of realistic, complex traffic scenarios. It's a very powerful traffic tool that's built in.
Yeah, I think this is really interesting.
Yeah. So we have a question online here. Will Octoscope make available Multiperf tool for UDP measurements on the Windows platform? Yes, Multiperf for Windows is in QA right now, so it will be coming out soon. It's currently available for Linux, and we'll be also adding it for Android as well. And another question from Ajani Nandan. In the PAL box, is it possible to configure virtual devices to different attenuations? This is to simulate multi-client at a variable distance. So the answer is you can use the transmit power, and we have control of about 15 dB range on the transmit power. And we do allow you to change the power of each virtual device, but the 16 stay pals each have their own control. I mean, no, sorry, not each.
In groups of 4.
4 has control. So they have 4 controls for power.
So yeah, so as Fanny was saying, so you can imagine the stay pals being used to create 4 users that are close, 4 that are further away, 4 that are further away than that, and 4 that are even further away than that, for example.
Yeah,
and
so stay pals have a full range because
those have the full range
of attenuation. But the virtual stations have about 15 dB of range. Yeah. Okay, we've got some raised hands.
Yeah, we have Ravi.
Yeah. So one of the RvR graphs that you showed for close and far antennas with no rotation. So on that graph, there is a, yeah, this is the one. So why is that there's a throughput difference below a certain RSSI level and there is no throughput difference on a certain RSSI level?
So I think at the high one, and I don't remember the settings for this, but this looks to me like it's probably pegged. So it's probably the case that when you're at a certain attenuation level, you're just not going to get any higher throughput, and you don't have any issue from the positioning sensitivity either. That's dropped you far enough, right? It's the same kind of thing that you see in a typical. Let me go back here. Like an RvR plot like this. If you looked at this plot as a function of, or in terms of the RSSI, you might actually see the RSSI dropping here, but the throughput doesn't drop, right? I mean, at some point you're getting as much throughput as you can get, and I think that's what you're seeing here. It's just pegging.
Oh, so when you're closer to the AP, then it doesn't make much of a difference.
Yeah, it's not going to matter that. I mean, it might if you, if you had the ability to get higher throughput or something like that. But however this test was configured, we didn't have that.
Okay, thanks. And one more question I have is, so right now you showed that AP as the device under test. So say if we need a station under device under test, will the stay-pal act as an AP or?
Stay-pals will not, but the PAL6 will. The PAL6 is a Qualcomm-based, access point chipset.
Hawkeye chipset.
Hawkeye chipsets. So this is a real sort of commercial grade access point, or can be configured to be one. In fact, it has tri-band operation. You can actually use it as an AP, simultaneously handling 2.4 and low and 5 high. Low and high 5. Sorry, what?
Oh. And we can also use the graphs and the statistics that you showed can be used for the AP as a station, as a DUT as well, right?
Correct. Yes, we have AP statistics as well.
Oh, okay. All right, thanks.
And then we have a question from Florin.
Hello, can you hear me?
Yes.
First of all, thank you for this great conversation and presentation. Put all slides together, really valuable assets. And my question is here regarding the rotation stuff. Let's say from the real world scenario, we have an AP XYZ in the house or anywhere else, and we have customers traveling horizontally and vertically in the house, let's say. So going close and far from the AP on the horizontal axle and the vertical axle. Which of these rotational test beds would best represent this test scenario? Let's say RvR versus range or orientation. Which of these tests would close come to the real world scenario in this case?
Well, I think certainly, the rate versus range versus orientation, or either any of the orientation tests handles people coming close and far, in the horizontal plane. The vertical plane would be somewhat different. I mean, assuming that the access point is oriented in a sort of a normal position here. I mean, I suppose you could imagine, orienting the access point, rotated so that you could see what it looks like, in a slice through the vertical plane. But certainly the horizontal plane is handled by any of those rotation test cases.
It's actually a good question. And last week we did channel modeling, right? And we showed how a typical house model behaves with non-line of sight. So the different floor will just be non-line of sight. And the reflections could come from anywhere and reach the antennas of the device under test. So if you do the IEEE standard model for the house, that it does cover different floors and different rooms, right? But to Lee's point, we don't really have, like, if it's a dipole antenna, it has a certain field, so the field will differ, but in the end, it's multipath environment, and when the signal bounces, the polarization will change as it bounces off. So MIMO is a very dynamic environment, and the antennas on the other of the device at one floor with reflections from another, they'll still have to pick it up in their field, which for a dipole will be like a donut field on a dipole. So this still has to reflect and get into it. So with the multipath, I would say you're covering some of those scenarios. But okay, in some folks want to still test in the house, and that's okay. And we have some devices you can use, including our turntable and all the pals, to test in the house with the same software in a test house, and then bring the results and take a look at how well they match with the Octobox. So our customers test, they use about 80% of the time in the Octobox, and maybe 10 to 20% in a real house environment sometimes, to cover some of those other interesting scenarios.
I got it. Thank you.
So another question is, can we use Xchariot instead of multiperf? We don't support it. We used to support it, but it's an expensive tool, and we now have all the features of Xchariot. So we stopped supporting it because they're charging something like $10,000 for a license, and we're charging a lot less for a license. Actually, we're charging for the whole server, but it's much more reasonable than the Chariot. And we do a lot more, as you could see. The Chariot is an older tool, and it doesn't do all the statistics that we were showing you. So it's very hard for us to have the Chariot and all these, MCS, number of streams, bandwidth, congestion, all the other, there's like a list of 20 stats that we can show you, noise floors. There's a lot of information we haven't even shown you that we can give you with our own traffic tool, and so we no longer support the Chariot. I mean, we have customers who run it, and you can run it if you have it on your devices. We don't do anything to preclude you from running it. All right, folks, feel free to contact us, and we'll be happy to respond.
All right. Thanks, everybody.
Thanks, everyone.